to recording. Okay, thank you. So what I'm saying is that you have a center of mass of positive charge here. You have the negative charge there. You have a electric dipole moment. Okay, you have an electric dipole moment for the water molecule. And that will be useful for many purposes, okay? I need to go to the next page. It's not moving. Okay, so this uneven distribution of charge gives the water molecule the nice property that it could attract positive charge as well as negative charge. And that's why in the dry weather, in winter, even if you push the button of the elevator, sometimes you get a shock, okay? Because you don't have enough water molecule in the atmosphere to take care of all this extra charge around, okay? Accumulating on the button, and then you put it back, and then you get a shock, okay? And more practically, this gives water the property of being a very good solvent. It can dissolve a lot of things because either charge sign, it could take care of it, okay? Positive attract to this part, negative attract to that part. It is a quantum mechanical result of this shape of the molecule, okay? And more importantly, as I already pointed out, you have the electric dipole moment. Then for this kind of molecule, the electron form the bond. The second part of the Born-Oppenheimer approximation is to allow this atom to vibrate. Here, in a cartoon form, I draw the one of the water molecule vibrational. These are called normal modes in classical mechanics. So this is one of the normal modes motion. So here is called the bending mode. So you have the oxygen and the two hydrogen on the side, so OH, so it's like bending. Okay, at the same time, the O goes up a little bit, okay? So here, for this mode, the take-home message is the following. The electric dipole moment is changing as the molecule is vibrating, okay? That is the key point I want to convey. Do you see that? It is not just a permanent, constant electric dipole. It is changing as the molecule vibrates. That's the key point, okay? Now, what is the important consequence for this fact? You have a varying electric dipole moment. It turns out that for such molecule, it will absorb electromagnetic wave at the normal mode frequency, okay? If only it has a constant electric dipole moment, not changing, then even it has an electric dipole moment, the selection rule will be zero. It will not absorb EM wave at this normal mode vibration frequency, okay? And then the normal mode frequency is 10 to the 13 hertz for this mode. That can be calculated from classical mechanics. It is in the infrared range. And it is this fact and this particular mode that makes water vapor a greenhouse gas. That turn water vapor becomes the bad guy, but actually water, innocent. It's just water, okay? Nonetheless, or by accident or by nature or by quantum mechanics, this particular mode falls into this range, and that will trap the radiation from Earth out into the atmosphere. Our atmosphere, if there are water vapor, it will absorb that, and then that will become a greenhouse gas. Another more infamous greenhouse gas is CO2. We will come to that later. So this ends this part about bonding in many different molecules. The next section is another application of LCAO, but very fascinating one. It's called hybridization. I'm sure that you have heard about this, and maybe you have memorized this to get good grades in your chemistry course. And I think it is time to have a better understanding, quantum mechanical one, for hybridization. In Chinese, it's called something like that. Okay, something like that. I look it up. Okay, so it is there are many types: SP, SP2, SP3. Okay. Of course, we will start with the simplest one. So SP hybridization is easier to handle, easier to understand. If you follow that, there will be no difficulty for SP2, SP3. So let's make it very clear at the outset what is hybridization. SP hybridization actually means the following. It is LCAO, linear combination of atomic orbitals. But the key point here is it is linear combining S and P from the same atom. Okay? That is to say, one atom will donate not only a S, not only a P, but a S and a P for bonding. That is the whole point. If you think about it, nothing fancy. Okay? I noticed there is a question. Did I answer that already? Howard? You can try different angles on Oppenheimer. Okay? Hello? Yes, right. So in addition, you have R1, R2, but by symmetry, you have an R there and you have an angle, and you look for a cloth, a energy profile, not only a line. You see? Okay, so that clean up the last part, all right? Now, hybridization. Let me repeat. The important thing is that we will see linear combination of atomic orbitals, but those orbitals are from the same atom. Okay? You may wonder what for. The answer is, by thinking about linear combining S and a P of the same atom first, that will prepare for some new orbitals that will be called hybridized orbitals for bonding with the AO of the other atoms. The key point is that it is convenient to think about it that way, and stronger bond will be formed, gain more energy. Okay, so that is the whole picture. So with this viewpoint, it is nothing strange, nothing new. Because in doing LCAO, we can include many atomic orbitals from the first atom and the second atom. Okay, so we already linear combine them. What is so special about hybridization then? So that is the question we will discuss now. It is better to do it schematically within a simple example. The simplest example I can imagine is this beryllium dihydride or something. Okay. So it is Be 2 hydrogen. And the chemist told us that it is linear. So I don't need to do all the angles. So this is linear. Okay, so I take this as a fact. It's a linear. So the beryllium will be in the middle, hydrogen on the left, hydrogen on the right. Okay. Now look at the atoms. Beryllium, ground state, 1s2, 2s2, all full. Okay. So if you think about it, it will not be chemically active. It's all filled. Low lonely electron waiting to form bonds. But the fact is, this exists. Then we have something that we want to explain, right? Then we look at the higher empty states of the beryllium atom. Those are the 2p state. They are different in energy, but not by much. Fact number 1, they are different in energy because it's not hydrogen, okay, but not by much. So in our mind, the picture is as follows, but it is only a picture. We will see how it unfolds within quantum mechanics at LCAO variational calculation scale. So in our mind, we are thinking about like that. How about this? Instead of being full, how about promoting? That is the story in your secondary school. How about promoting 1 electron to one of these empty p states? So I have a 2s, lonely electron. I have 1, I call it p, z, doesn't matter. Also has 1 electron. Thereby, this can pair with a hydrogen. This can pair with a hydrogen. It's possible to do this. Okay. Let's see how it comes out. So that motivated us to include for the beryllium 2 AOs, a 2s and a 2pz into the LCAO consideration. Then at the same time, hydrogen will have a 1s, but we have 2 hydrogens on the left and on the right. So let's take do some accounting. So we have 2 AOs from beryllium, 1 from left hydrogen, 1 from right hydrogen. Altogether, we have 4 atomic orbitals to start our linear combination. All right. So we are linear combining 4 AOs. Follow me? 2 from beryllium. Okay? Now, your mind should start cranking. Okay? You have a linear combination as a child wave function. What do you get? You will get a 4 by 4 matrix, right? Right? Then you will get 4 MOs, 4 energies out. Then you count. I have 1, 2 electrons from beryllium and 1 from the left hydrogen, 1 from the right hydrogen. I have 4 electrons altogether. That will form the 2 lower MO, leaving these 2 empty. There may be bonding. Then, now that's the whole picture. Okay, do you follow me? This is good physics without doing math, okay? Don't think that doing physics, you must have lines of mathematics, okay? We have done that, and then we are making use of that. That is applied physics here, okay? As the course title suggests, okay? So let's set this up without really doing the math. So schematically, I will have a 4 by 4. So I'm trying to line up the 1, 2, 3, 4 as follows. So I have a hydrogen on the left, 1s, beryllium 2s, beryllium 2pz, hydrogen 1s on the right. Okay, similarly for that. So in our formalism, we will call this 1, 2, 3, 4, and then we will have H11 minus ES11, etc. Do you follow me? So now if you do that, in principle, we know how to fill in this 16 matrix elements and then diagonalize it or find the eigenvalue E, we get the 4 MOs. So basically in our mind, this is done, okay? Now, the first appreciation is that we are done without invoking hybridization. Do you get the point? You give me this 4 as the ingredient, I set it up, done, okay? Then why do we need hybridization? That is the next question, right? And is hybridization something very strange? But we are already done. So hybridization must be already embedded. Okay, so next we need to explore where is hybridization stuff here. Okay, no new physics, that's the point, but there's new thinking that can help us in many different molecules and solids. You know, semiconductors are formed by sp3 hybridization of the silicon atoms. Okay, so let's move on. So we are basically done without hybridization idea. But now I would like you to focus or imagine, I have not written down anything, this block. Now, this block is related to the 2 by 2 block of the beryllium atomic orbitals. All right, so focus here for the moment. For that block, I take it out here schematically. We have beryllium 2s, beryllium 2p. The key point is from the same atom, all right? So let's draw a picture out. The beryllium 2s will be like a ball, is an S. The beryllium 2p is like a dumbbell, like that, okay? They belong to the same atom, so I emphasize that I draw it starting from the same nucleus, and that's the main point for hybridization, all right? And now, we can change bases. When we have a matrix, we can change bases, right? Okay, this is the key point. Get that? Okay, so now we are exercising this right of changing bases. What are we doing in changing bases? How about this? Okay, the next step will be hybridization, the name, okay? Now, I have this in my 2 by 2 block. I want to change the bases by adding the beryllium 2s and 2p and subtracting them. Okay, now I'm not writing down the normalization 1 over square root 2, things like that. Okay, that will come next if you want to do it quantitatively. But the idea is just changing base for this particular atomic block. All right, so let's look at what is the resulting picture. I add them together. So I am adding this S to this P. What does it mean? When I see regions that are both positive, it will be more positive. When I see a region that is negative and positive, they subtract, okay? Get me? So if I do this, it will give me something like that. Do you see the point? The other combination minus, I will get something like that, okay? Now, do you see that this so-called hybridized sp orbital for beryllium, it is focusing its wave function to the right. And the other one is focusing the wave function to the left. Okay, do you see the point? Is that okay? I'm not changing any fundamental physics, making assumption, things like that, okay? I'm just changing basis. And usually you don't see this picture, you see these two pictures drawn together. So here it is showing in a pictorial way two so-called sp hybridized orbital. One is this small blob with this big one pointing to the right, basically. One is this small blob with this big chunk pointing to the left, okay? Quantum mechanically, it is forming this two linear combination, okay? So if that doesn't ring a bell in your mind, the simpler picture is as follows. Always think about an atom as a finite well. That is a very good picture in mind. So I have a ground state that will be my S. I have a first excited state that will be my P. How about I add this to this, okay? So the positive side add to the positive side will be more positive. There is a positive side compete with the negative thing that will give me some negative part, okay? If I draw the probability square, it will be something like that, okay? You see the similarity to this thing, okay? Similarly, if you subtract that, okay? This minus this will put this onto the positive side. It will go the other way, okay? See my cross? It will give this one, and that is like this one, okay? So keep this simple-minded finite well picture in your mind, and hybridization is nothing anymore, okay? Now, we were emphasizing that there's nothing fancy but changing bases. But we have a 4x4 matrix to start with, okay? You may wonder, changing bases, so what? What for? What for, all right? Now, follow me in concept. We form this sp hybridized number 1, changing bases, this one, and we know that it is pointing to the right. So we know this will have more to do with the hydrogen on the right. Similarly, this will have to do with the hydrogen on the left. Okay, they will form good sigma bonds, right? Okay, so after changing bases, this is the idea. I have a sp hybridized number 1, which is to form a good sigma bond with the hydrogen 1s, hybridized state number 2 to form a good sigma bond with hydrogen number 2, all right? So what happened to our 4x4 matrix then? originally, we have the beryllium block here. We add them, we subtract them, and form two new ones. One is called number 1, that will form good bond with this. One is called number 2, that will form a strong good bond with the left hydrogen, okay? So after we change bases, we rewrite the 4x4 into this form. We no longer have beryllium S and P. Instead, we have hybridized number 1, sp hybridized number 2. Okay? I put the number 1 next to the right-hand hydrogen because of this picture. I can interchange the role, doesn't matter. Linear coupled equations, right? So which one I put as the 1, 2, 3, 4 equation, it doesn't matter. Okay, so this is the realization of that. So now I would like to focus on, for example, this picture. This picture tells us the following. After I do the hybridization, I have some advantage. The left hydrogen and the hybridized number 1 will form good overlaps. So basically, hybridized number 2, the one pointing to the left, will have a strong overlap that I don't need to know what it is. I just use a symbol, okay, delta, with the hydrogen on the left-hand side. So this is a good, strong overlapping hopping integral, so-called. This will be delta star. And this energy should be different from the beryllium 2s and beryllium 2p. We have to calculate that. We can calculate that after we know the linear combination. Okay? Now here's the main point. The hybridized number 2 will form good bond with the left hydrogen. The hybridized number 1 will form a good bond with the right hydrogen. Okay? In principle, after you do the changing bases, you can calculate all the matrix elements again because you know the initial 4x4 matrix. The whole physical picture is that after doing the hybridization, the left hydrogen is too far from this one to have any coupling. So this will be approximately 0. Similarly, this hydrogen, you have to go past the middle atom, and then that may be 3 angstrom away for the next hydrogen that is too far. So it is approximately 0. So all in all, I want to approximate this off-diagonal block to be 0. All right? Now, suddenly we can solve the problem. This is a 2x2 push up, push down. This is a 2x2 push up, push down. And that is a nice picture. That comes from the original 4x4 LCAO picture. That's why at this point I said we are done. But more fancy analysis tell us that it is equivalent to such a problem. Well, at least approximately, okay? And therefore, we know how this thing can be formed, okay? That will be the bond here. This will be the bond here, okay? So, by doing so, focusing the wave function, the delta overlap integral will be stronger, and thereby the pushing will be more, lower and higher. But it is the lower one that will be occupied, the left one and the right-hand one. Therefore, this will form this bond. The lower corner block, I mean this block, will form the right-hand side bond, and therefore we have this linear molecule, rather strong bonding, okay? And that explained the hybridization. This is sp hybridization, okay? Now, there is a deeper understanding to see that hybridization is nothing. I mean, by nothing means it is not a separate topic. It is embedded into the LCAO thinking. For example, we start off with beryllium 1s with 1 electron, beryllium 2p with 1 electron. How can we write this 2 electron wave function in a legal way? We don't know which electron is which, right? So we have to write something like this, Slater determinant, okay? Now, how about this? We make linear combination and we write this thing. So we form linear combination, This will be the hybridized one. Here I do it formally. I introduce this 1 over square root 2 for the following reason, okay? Now, we are only having an S and a P to form 2 sp hybridized state. The S character will have to be evenly divided into these 2 states. It will not bias the left or the right one. It shouldn't, right? Okay? So therefore, in each of these linear combinations, I know that at the end, there will be 50% character of S in each sp hybridized state, okay? And the probability is the coefficient squared. Therefore, I know this A must be 1 over square root 2. So the square root is half, 50%, okay? So that is the reason, basically. And after working out the other coefficient, I know that it's also 1 over square root 2 because the whole thing should be normalized. So I have these 2 linear combinations. Again, I have 1 electron in here, another electron in there. How can I write the legal wave function? Slater determinant again, okay? So now I have 2 ways to express the same thing. I have this phi12, this psi12. I have this phi12, okay? Are they the same? Then I work out the exercise, Slater determinant, okay? I write it out. These are the linear combinations. So I really write down the linear combinations. I multiply everything out. You can easily show that the second way using hybridized orbital to write the 2 electron wave function is the same as the original way to write the 2 electron in 2 atomic states. That's what I say. Hybridization is nothing fancy and nothing worth memorizing. Generation of students somehow just memorize all this funny thing, okay? But we have one umbrella, quantum mechanics and LCAO. And now we have this already embedded, all right? So, and this page echoes a sample question this week. In the sample question, the TA will do SP3 hybridization, the angle between two hybridized state, the famous 109 degree, okay, the tetrahedral thing. But here is the basic idea, okay? So this page gives you the formal way to construct sp hybridized state. Let's start. Beryllium. We have 1, 2s, and then 2p atomic state. The linear combination should be, formally, I have A, okay? I have another coefficient A here, okay? But I already argue the S is to be evenly donated to the sp hybridized orbitals, 50% there, 50% there by probability. Therefore, the probability amplitude, I have this already known, okay? This is why we have this 1 over square root 2 here. Easy. If you are doing sp3, there will be 4 sp3 hybridized state. The S will be evenly donated to the 4, so the S coefficient will be 1 over square root 4 in sp3 hybridization, okay? So here, let's focus on this simple case. So the remaining coefficient to solve is this 2 C1, CA and CB coefficients, okay? We know the answer. This is plus square root 2, this is minus square root 2, but we want to know how to find them out systematically. Now, the hybridized state should be normalized by itself, okay? So I know this, I don't know this, therefore, let's exercise normalization, okay? By normalization, I have this atomic state being 1 already. This is normalized. This is also normalized. So I have an equation to solve for CA. And we will get, since this is half, 1 minus half is half, so CA is plus square root 2, okay? So up to here, we find the first combination. This is the one pointing to the right, okay? How about the other one? So what is remaining is this coefficient. How to do that? With the first one known, then we want to exercise the following property. The hybridized orbital should be orthogonal to each other, just like the atomic orbitals by themselves, all right? By orthogonal, we mean mathematically orthogonal. It's a definition of orthogonality of the functions. By that, we mean the following. We want this to be 0, okay? That gives us the condition to solve for the remaining coefficient, okay? So we have this phi A star phi B theta must be 0, okay? So, but we know this, we multiply into this one, all right? Now, the cross terms are automatically 0. Phi S multiply phi P, because they are atomic orbitals of the same atom. By atomic physics solution, they are orthogonal, okay? So we don't have the cross term. The only remaining term is this part multiply into that part, pick up the coefficient unknown, but this is 1, okay? So thereby, we can solve for the remaining one. This is minus square root 1 over square root 2. So at the end, we don't need to guess what they are. We constructed the sp hybridized orbitals. All right. Now, how are they lined up in real space? They are mathematically orthogonal, but doesn't mean that they have 90 degrees in real space. This orthogonality is about the function. In space, we already seen they are 180 degree spread, okay? One to this side, one to that side, okay? How can we see that easily? It is easy to see that easily. The lazy way is the following, but I like the lazy way, okay? There is a complicated way to look at the charge distribution, but the lazy way is that S, no direction, is a ball. Okay? But you see a P Z. So this is like a unit vector, well, pointing at plus Z. Similarly, you see this term, this must like a unit vector pointing in minus Z. The first term S has no direction, okay? Therefore, you know that one is like that, one is like that. In real space, they are 180% apart. That is the point about spreading out the beryllium 2 electrons to direct them into different directions so that the Coulomb repulsion is also minimized. And then by doing so, good overlap with hydrogen on the other side, strong covalent sigma bond are formed. All right, so that's the story about beryllium H2, okay? So this is the sp hybridized state. So that will give you enough background to go through the sample question this week. I have to stop here. I think we overrun a little bit. There are still sp2, sp3, and then the last part will be, in molecular physics, will be to allow the atoms to vibrate again. Remember, the full Hamiltonian has the kinetic energy of the nuclei. We ignore it for the moment. We do the electronic part, C bonding, LCAO, AO, MO help us C bonding. After bonding, we have the bonds, and these bonds are the springs. So we need to take the whole Born-Oppenheimer treatment out again and let the nuclei move. They can vibrate, they can rotate. Then we will discuss the rotational spectrum and vibrational spectrum of molecules. They are the fingerprints of molecules, just like atom has fingerprint atomic spectrum, okay? That will be the last part of our course, all right? So I will end here today. If you have questions, I will stay to answer your question. Let me look at that, last chapter, okay. So let me first stop sharing and then see what is the question.